Honors Pre-Calculus students, welcome to your 8.3, 8.4 notes. We're going to take a look at matrices, have a few more little applications we're going to do. We're going to start with something called the determinant, and let's take a look at it. So every square matrix, keyword there, can be associated with a real number called its determinant. So the determinant of a matrix like the 2 by 2 matrix you see here, A, B, C, and D, would be, another way to write that would be to, instead of using the matrix symbols, use what look like absolute value bars, but that's not what they mean, and then do A times D minus B times C. So it's basically main diagonal minus the opposite diagonal. And by the way, this process we're using only works for 2 by 2 matrices. There are ways to find 3 by 3, 4 by 4, etc., but it's much more complex. It's not something we're going to worry about a whole lot by hand. So let's take a look at this. Find the determinant of the matrix. That would be 3 times 0. These are really fast problems, you'll see. Minus negative 7 times negative 5. So that would be 0 minus 35. So negative 35. Why don't you do this? Pause the video and find the determinant of 2 and 3. And then once you found it, hit play and compare your answers to mine. Alright, welcome back. You can see what I've found on 2 and 3. Number 2 was 0. Number 3 was negative 3. Those are determinants. We have some applications for those. We don't get real in depth with those, but maybe in other classes at some point you will. For now, we're basically learning some of the basics. So let's take a look at a few examples of those. For matrices A and B, find the determinant of A, the determinant of B, and then the determinant of A times B. So let's start with A. Pretty straightforward calculation here. A would be negative 2 times negative 2, that's 4, minus 1 times 4, which is again 4. That would give us 0. Alright, let's look at matrix B. The determinant there is 1 times negative 1 minus 0 times 2. So our determinant for matrix B is negative 1. Finally, let's go ahead and find the determinant of A times B. Well, before we can find the determinant, we're going to have to go ahead and multiply. So I'm going to have negative 2 times 1 plus 1 times 0. Then row 1 times column 2, that's negative 2 times 2. 1 times negative 1. Now I'm ready for row 2, that's 4 times 1 plus negative 2 times 0. 4 times 2 plus negative 2 times negative 1. So matrix AB would be negative 2, negative 5, 4, and 10. Alright, so let's go ahead and find the determinant of this matrix. And that would be negative 2 times 10 minus 4 times negative 5, that's negative 20, minus negative 20. That's really interesting. So the determinant of matrix AB was 0, and the determinant of A was 0, the determinant of B was negative 1. Could there be a pattern there? Maybe that should require some further exploration. But for now, we're going to move on to something that looks a little different. Again, we're using determinants, but we're going to do some basically some evaluation so that we can solve for an unknown. In this case, that's x. So we're going to use the determinant. We're going to have x plus 4 times x minus 5 minus this diagonal, which would end up being plus 14, equal to 0. Now we're going to go through and solve this for x. So we'll have x squared plus 4x minus 5x, so that's minus 1x. And then we have minus 20, but we also have a plus 14, so I'm just going to write that as minus 6, equal to 0. So x minus 3 times x plus 2 equals 0. So what we'd get there is x equal to 3 or perhaps negative 2. We have two possibilities. Alright, kind of a similar problem on number 6. A whole bunch of variables here. We're just going to follow with the pattern we know, what determinants mean. So we'll have w times c times z. So we'll just write it that way, WCZ, why not? Minus CX times Y, so CXY, equals, And then I'm going to go ahead and evaluate this determinant as well. So this is C times WZ minus XY. Okay, let's go ahead and for the sake of trying to show that these two sides are exactly the same, let's factor a C out of this first term, and we could go the other way and work with the right hand side instead. That would be fine, but we could see very clearly that when we factor out a C, we have the exact same thing on both sides. And yes, I'm okay in this type of problem for you to use both sides. It's not exactly a trig identity situation, so we're fine. If we wanted to work with one side, we could, but that's not really what we're working on today. As we move to the next set of questions, you're going to need to get your graphing calculator out, and this is one thing that Desmos doesn't do very well, to my knowledge, is working with matrices, so you definitely want to have your actual fancy TI-84. So what we're going to do is enter a matrix, C is what we're calling it here. We can call it whatever we want on our calculators. We're going to enter matrix C on our calculators and then find the determinant. Now here is the key to all this. If you hit second and then above this x to the -1, your inverse button, you can see it says matrix. So we're going to enter that matrix, and we're going to go over to edit. Now I know this is called matrix C. It really doesn't matter. I'm going to edit matrix A. Now this matrix over here, the dimensions are 3 by 3, so I'm just going to hit 3 and 3, and I can hit enter to go from one entry to the next, and then I'm just going to enter, and I can enter the first row 0, 2, 1, and I'm just pressing enter in between each button or each number I should say, and it's pretty simple to create that matrix. There it is, 0, 2, 1, 3, -1, 2, 4, 0, 1. Now from here I want to quit. That takes me back to my home screen, and I'm going to go back into the matrix menu, and I'm going to go to math, and you see the very first option up here says DET, so we're going to choose that DET, and then it's saying you want to find the determinant of what, so we're going to go back into matrix. Remember we saved this as matrix A, so we're going to choose A, determinant of matrix A, and all you have to do is press enter, and voila, you have yourself a beautiful and simple answer, 14. Now again, we could do that by hand. There is a possibility to do this. There are a couple of different ways you could handle it. It's not something we're going to spend a lot of time on though. We have machines that can do that for us. One of the big reasons that we consider determinants of matrices is we can use them to find inverses. Now before we get into all of that though, we want to talk about what are inverses. That just simply means that if you took a matrix A times its inverse, or the other way around, the inverse of a matrix times A, it would equal I. Now I is the identity matrix, and in this case the identity matrix, if it's 2 by 2, it's 1, 0, 0, 1. If you increase to a 3 by 3 matrix, it would look like this. It would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's the identity matrix. Okay, and if again it's ones in the main diagonal, zeros everywhere else. So if I multiply these two matrices together, and I get an identity matrix, I know that A and B are inverses. If I get something besides that, then I know they're not inverses of each other. So let's go ahead and try that. I'm going to rewrite these two matrices, -1, 2, -1, 1, times the matrix 1, -2, 1, -1. Alright, so when we multiply, we'll get -1 plus 2. We'll get 2 minus 2, -1 times 1, so -1 plus 1, and then we get 2 minus 1. And that gives us 1, 0, 0, 1. Folks, right there, that's what you're looking for, the identity matrix. And so by doing this work, by multiplying the two together, we have proven that A and B are inverses. Alright, there are other ways to find inverses. We're not just always given two inverses. Sometimes we have to find them. Now, our calculators can do that. We'll get into that in a minute, but we want to show you where this is all coming from. So again, we're going to stick with the 2 by 2 matrices, solving them by hand. Here's the setup. It's kind of a weird little situation. It's not a little thing you need to memorize, but if you're finding the inverse of a matrix that looks like this, where you have A, B, C, and D, you need to find the determinant, because you're going to use the reciprocal of the determinant, times, and then notice how this new matrix is reorganized. A and D trade places, B and C change signs. Okay, interesting. So what we're going to do is start by finding the determinant. We need to do this on each of these. You can't really find an inverse if you don't know the determinant. So in this case, that would be 6 minus 2, which is 4. So to find the inverse, I do the reciprocal, which would be 1/4, times, and then we'll trade A and D. So 2 goes here, 3 goes here, and then change the sign of B and C. So instead of -1 and -2, it would be +1 and +2, and then we just simply multiply. 1/2, 1/4, 1/2, and 3/4. There's your inverse. Alright, let's take a look at the next one. The first thing we want to do is find the determinant. So we'd have 15 minus 3. And of course that would be 12. And to find the inverse, we would do 1/12 times that reorganized matrix. Trade A and D. Change the sign of both B and C, and we would get this. Now I know these numbers aren't really pretty, they're kind of ugly fractions, but we're okay with that, and it would work. And here is your inverse. Again, if you wanted to check to see if these are truly inverses, you could just multiply them. It wouldn't matter which order you multiplied them. You should get the identity matrix. Okay, why don't you guys pause the video again, find the inverse of number 11 on your own, and then compare your answer. Alright, welcome back folks. You can see my work on number 11. Again, beautiful fractions, 5/23, -1/23, 3/23, and 4/23. Always love those. Alright, we're going to do a little work with the calculator. Now what I have done, I've actually taken the liberties to go ahead and punch in this 3 by 3 matrix. You can see if I put in matrix A that I get the matrix that you see right over there. Okay, and what I'm going to do with this is I'm going to actually find the inverse. So what I need to do, it's actually really simple. If I go second matrix and choose matrix A, and then remember when we talk about, I called this matrix A. When we talk about A inverse, we'd write it like this, right? So all I need to do is punch that button on my calculator, this x to the -1, and then I press enter. And look what we have there. We have our inverse matrix. The only thing I would say is that we have a whole bunch of decimals here. When we can, especially with inverses, it's likely that we can get some, values that look a little better. So I'm going to do what I call math fracking. We're going to math frac this thing. And so all you have to do is hit math and frac, and it changes those decimals into beautiful fractions that you see here. So we have our solution right there. Alright, 2/5, 9/5, etc. Pretty simple process, isn't it? I think so. Hopefully you agree. Alright, we're going to do something, some more work on the calculator. Now I have to tell you, this is probably, in my opinion, the most valuable use for matrices, and that is being able to solve systems. Now watch how easy this is. I'm going to write this as a augmented matrix that looks like this. I'm going to punch that matrix into my calculator. And due to YouTube limitations, I'm going to have to switch to a 2-part video here. So as you enter this matrix, go ahead and switch over to part 2 of the video and get the rest from there.